Good morning, folks.
Good morning.
Good morning.
How y'all doing today?
Pretty good, pretty good. How's the weather treating everybody?
Lousy.
We're getting close to the weekend, so hopefully you get a little breather here. All right, just letting a few more folks into the class here. Okay. One more. Okay, well, welcome back. Good morning to you. As we rub the sleep from our eyes, let's get ready to continue a conversation in chapter 2, which is chemistry chapter. If you don't already have it up on your machine, please be sure that your textbook is open and ready to go, because you never know, I might ask you a question where you really need to be looking at your textbook. Okay, so welcome back. Let's continue here. I'm going to share my screen with you. Okay, and here we have the notes we finished with from last time. Okay, before I continue taking notes, let me just pause and ask anyone if there's any questions right now about content that you've been reading, about things we've been discussing, anything bothering you with the technology of the course. Is there anything I can help you with at this time? Okay, everybody's quiet, so we'll continue. So we've been talking about atoms and characteristics of atoms, like atomic number and mass number and things like that. And then we switched into this idea of chemical bonds, and we said that chemical bonds are actually quite a bit similar to each other, right? Three sides of the same triangle. And then the last thing we started with at the end of last class was talking about the definition of an ionic bond. And I drew this little diagram up in front of you here where we have 11 protons and 11 electrons at the sodium atom, 17 protons, 17 electrons at the chlorine atom. Okay, so this is where we're at. And what we're trying to do is explain to you how the attraction between sodium and chlorine comes about. Why are sodium and chlorine attracted to each other? Because right now in the drawing, I'm implying that these two atoms are in fact separated from each other. Okay, so if we refocus our thinking on this, here we have a sodium atom with 11 positively charged particles and 11 negatively charged particles, which means that the atom itself is electrically neutral. Okay, that comment there over by the side, atoms are defined as electrically neutral. Well, if sodium is electrically neutral and chlorine is electrically neutral, then there's really no attraction between the two atoms. There's no reason for them to sort of come together and associate with each other. So while these atoms are defined as electrically neutral for the purposes of chemical theory, in reality, we know that atoms do not maintain their neutrality, because if they did, molecules would never form. And if molecules never formed, you and I wouldn't be sitting here having a conversation, would we? Because our bodies are made of gazillion molecules, right? So without the molecules, life is not possible. So why do these two atoms come together? Again, you will not be an expert on this from one chapter in one biology course. You're not going to be a chemistry expert. But if you have your textbook open, please turn to figure 2.4. Figure 2.4 on page 34. Figure 2.4, page 34. And what we'll talk about here is a couple observations. Okay. So let me see here. Okay. All right. So Just looking at who's online with me at this moment. Okay, so let me ask Sierra Rosenberry. Sierra, can you please unmute your microphone and say hi?
Hi.
Good morning, Sierra. Sierra, do you have your textbook open on your computer?
Yeah, I do.
Okay, great. So on page 34, figure 2.4, Sierra, when you look at panel A of that figure, on the upper left of panel A, you see a green sodium atom, Sierra, my question to you is this: how many rings of electrons are around the nucleus?
There's 3.
Okay, great. Stay with me, Sierra. And Sierra, in the third outermost ring of sodium, how many electrons are there?
Just 1.
Just 1. And I'm not sure, Sierra, if you've had chemical theory in any other courses, but would you be able to tell us how many electrons should be in the outer ring for sodium to be stable?
I'm gonna take a guess and say 8.
Sierra, good guess. You're absolutely right. Okay, so without going into a long-winded conversation about atoms, because this is not a full chemistry course, right? If this was a full chemistry course, we could spend a lot of time on this. But what I'm trying to highlight for you, and thanks, Sierra, you did a great job, is the reality that there are electrons obviously spinning around the nucleus of atoms, and atoms tend to be most stable when there's a certain number of electrons in each one of the rings, each one of the green rings you see, each one of the green shells, if you see. Okay, and so you notice that the third shell in sodium only has 1 electron, and sodium would really like to have a complete outer shell of electrons. It would like to have 8 electrons there. Well, there's only 1. So for sodium to actually be stable, the atom could do one of 2 things, and I'm going to say it this way: either the atom could try to pick up an additional 7 electrons from some other source in the environment, or it could simply get rid of a single electron, destroy the third outer electron ring, the third outer electron shell, and be more content with 2 electron rings. Okay, so let me ask you a pragmatic question in the chat window. Okay, here we go. If you, as a human being, could be made happy by acquiring 7 objects you don't have, or by getting rid of 1 object you do have, which is the quicker path to happiness? What would you say, folks? Okay. Doesn't it seem quite a bit more pragmatic, reasonable, efficient, that if I can be made happy, which, you know, I'm using that in quotations because atoms aren't happy, but they're either stable or not stable. They're either stable or not stable. That it's a bit more pragmatic to simply get rid of an electron and become stable that way, rather than trying to acquire 7 electrons from other atoms in the environment. It's just easier to do that. And my point here is that atoms that you see on the periodic table of elements are like human beings in the sense that they have a personality, they have characteristics. Okay, and so the personality of some atoms, like sodium, is that they get rid of electrons in order to become stable. And other atoms, like chlorine, actually accept electrons to become stable. If you look, figure 2.4, panel B in the middle, you notice that, chlorine is being color coded here as yellow. Obviously, atoms don't actually have a color, but it's color coded in the book, so it looks pretty and you can look at it. Do you notice that the chlorine atom has 3 rings? The outermost ring of electrons has 7 electrons, so it's only deficient 1 electron. Wow, that seems kind of a match made in heaven, doesn't it? Because chlorine could be made happy by acquiring 1 electron or getting rid of 7 electrons. And so when sodium and chlorine are near each other, they have a good relationship, okay? They have a good interaction. So without getting into quantum mechanics and other things that we're not really ready to tackle at our stage of our education, let's describe the ionic bond this way. Okay, again, because of a desire to become stable, sodium will eject a single electron from its 3rd outer ring of electrons. It will eject one it will eject 1 electron, okay, in an attempt to become stable. All right, so follow the math with me if you would, okay? If sodium ejects an electron, then that means there are going to be 10 electrons around sodium rather than the 11 we started with, okay? Now, if we have 11 protons and 10 electrons around sodium, obviously there's an imbalance, okay? If we're on a seesaw, there's a little bit of an imbalance. That means we have 1 additional positive charge than we do negative charge. So that means that the overall charge on the atom becomes +1. This is the overall charge on the atom. Okay, so question in the chat window, folks. Is this making sense how I'm describing it? Are you able to follow what I'm trying to say to you? Do you have any questions? Sodium has ejected an electron, so it can get rid of the third outer ring of electrons you see on figure 2.4. And by doing so, sodium becomes more stable. Atoms like to be stable, right? We like to be comfortable as human beings. Atoms like to be stable as human beings, as sort of the equivalent of a human being. Okay. All right, so if we continue our description here, all right, so sodium ejects an electron. Chlorine, as we've shown to you on page 34, it only needs one additional electron to fill its outer shell, and then it will be very content. So chlorine will happily pick up the electron that sodium has gotten rid of. So we'll then have 18 electrons around chlorine. So that means I now have an imbalance also of protons and electrons around chlorine. I have 17 positively charged particles and 18 negatively charged particles. I have 1 more negatively charged particle than positive, which means the overall charge on chlorine becomes -1. In essence, and let me write this down over here. When sodium ejects 1 electron and chlorine accepts 1 electron, these atoms become ions. These atoms become ions, right? An ion, as you may remember from reading the early pages of chapter 2, are electrically charged atoms. Okay, It is, and then at this point, we have to rely on the old phrase you probably learned since elementary school or middle school, that opposites attract, right? Oppositely charged particles are attracted to each other. So what I'm saying to you is, when these atoms take on an electric charge, when they become ions, this is the foundation for the formation of the attraction that pulls the two atoms together to form a molecule, which is sodium chloride. Okay, now you could certainly ask a very reasonable question, which is, why do oppositely charged particles attract? And you know what? You're now getting into an area that science really can't answer. It's kind of like asking, it's kind of like asking why did God design oppositely charged particles to be attracted to each other? Well, nobody really knows the answer to that. In the same fashion, as you look out your window and look up at the sky, let's be fanciful for a moment. My sky is kind of like a dull gray out there, but maybe yours is bright blue on a pretty day. If you look up into the sky on a bright, pretty day, you could ask the question, why is the sky blue? And I can answer that. The sky is blue because the molecules of the atmosphere reflect blue wavelengths of light. But here's a separate question. Why was the sky designed to be blue? Well, I don't know. Only God or whoever you believe in could answer that. In the same fashion here, science observes that particles like sodium and chlorine that take on opposite charges, they are attracted to each other. Why it is designed to be this way, we can't really say, but it is. Okay, we observe it, we measure it, and this is what our current theory understands to be true. Okay, so this is the foundation for the creation of an ionic bond. When one atom donates electrons, another atom nearby accepts them. These atoms ionize, they have opposite charges. That's the foundation for the attraction. Do you have questions? Okay, now in terms of our course, I will expect you to have some basic chemistry knowledge in your brain and to be able to reason in certain things that we're having a conversation with here in class, but I won't be throwing any complex chemical reactions at you. That would be really inappropriate because we're just not going to get that sophisticated in our course. Okay, so please understand the conversation that we're having. Do your best to study and learn vocab, but don't worry about any complicated chemical reactions and things like that. That will be left for your future chemistry courses. Okay, do you have any questions you'd like to ask right now? Okay. All right. Okay, folks, let's go on to the next topic. The next topic is on page 35 is covalent bonds. Okay, so covalent bonds are highlighted. They are described to you on page 35 with words, and on page 36 there are some examples of covalent bonds that are drawn out here. By the way, the different atoms that are drawn with the nucleus and the rings of electrons around them in your book, believe it or not, let me say a couple things. The way your book is presenting this content is very reasonable for a beginner, very reasonable for a beginner. But I will say this, that the pictorial description, the graphical representation of an atom that you see on the pages of chapter 2 represent a description of the atom that was developed, well, basically 100 years ago by a man by the name of Bohr, B-O-H-R, and it's the Bohr model of the atom. Strictly speaking, in modern chemistry, we don't quite think about atoms this way anymore. The more current and contemporary description of atoms is from a field of thinking called quantum mechanics that you may have heard of. Quantum mechanics is a theory. And based on that theory, I mean, to understand quantum mechanics, you really have to understand calculus. Okay. So because most of our students taking this class have not had calculus, and probably many of you pray you never will have to take calculus, we don't describe atoms with the most current contemporary theory. Okay. That doesn't mean what you're getting is irrelevant. It just means that it's a different way of thinking about things. Okay, Walter, I saw your comment to me. I understand. Do the best you can. Okay. Okay, folks. So covalent bonds. Let's describe what these are. Covalent bonds are a covalent bond is an attraction created when atoms share electrons. Okay. So the key definition, the key terminology in an ionic bond is when one atom donates or transfers an electron. But with covalent bonds, the attraction is created when atoms share electrons. So remember, I made the point that atoms are kind of like people. Atoms tend to have certain personalities, right? Sodium has the personality that it wants to get rid of an electron to become stable. Chlorine has a personality that it wants to accept an electron to become stable. There are other kinds of atoms like carbon atoms, oxygen atoms, hydrogen atoms that seem to have a preference not for giving away or accepting electrons entirely, but for sharing the electrons with other atoms, okay? And so this opens up some kind of interesting possibilities here, okay? There are two main types of covalent bonds. We have the polar and nonpolar covalent bonds. Polar and nonpolar covalent bonds. And so we need to talk about each one of these. And I'm going to once again draw a little bit of schematic here in order to describe these things. Okay, so, all right, let's do this. Okay, so I'm going to describe the nonpolar covalent bond situation first, and I'm going to put nonpolar here on the right. Okay, so an example of a nonpolar covalent bond would be, well, the example that I'm going to give you would be a carbon-carbon bond. Okay, a carbon-carbon bond, where that little dashed line between the two carbon atoms is a graphical depiction, a representation, a symbolic representation of the bond. Now, nonpolar means that the atoms participating in the bond equally share the electrons. Equally share the electrons, okay? So if I could highlight what I'm talking about, if I have two carbon atoms that are going to share their electrons equally, and please give me a little bit of artistic license, meaning because I'm a very bad artist, if I were going to depict the motion of the electrons that are being shared between these two atoms, here's how I would roughly do it. So I'm going to draw the motion of electrons on your screen at this time as a dotted dash line, trying to indicate the motion of the electrons. And here's roughly what we're suggesting. Here we go. I'm a very bad artist, but what I'm trying to convey to you is the electrons spend roughly 50% of their time around the left carbon atom and roughly 50% of their time around the right carbon atom. So when we say that the electrons are shared equally up here, okay, when I make this statement, I'm not saying that you take an electron like a pizza and cut it in half. No, you can't do that. You You can cut a pizza in half, you can't cut an electron in half. So we're not literally taking an electron and cutting it in half, but I can share the amount of time the electron spends around one atom versus the other atom. Okay, so roughly 50% of the shared electron's time will be around the left carbon. The other 50% will be around the right carbon. This is what we mean by nonpolar. Okay, so certain atoms prefer to make these kinds of bonds. And I will say right now, as sort of a punchline, typically when you're dealing with nonpolar covalent bonds, what do we notice? One of the common features here is that the two atoms participating in the bond are identical, right? It's carbon on one side, carbon on the other side. It's kind of like having a tug of war with a clone of yourself. A tug of war with a clone of yourself. Okay, think about what that would mean. All right, so let me just put that down here. Notice both atoms are the same. All right, so that would be the nonpolar covalent bond scenario. In contrast to that, or in addition to that, there's another scenario, which is the polar scenario. Okay, so polar scenario, I want to highlight for you because your book is showing it to you. Figure 2.5, page 36, figure 2.5, page 36. Panel E there at the bottom, do you see an oxygen atom and a hydrogen atom? Okay, that is an example of a polar covalent bond. And so let me draw it this way. First off, the symbolic representation is H bonded to O, hydrogen bonded to oxygen. Polar means that there is an unequal or uneven sharing of electrons. An unequal sharing of electrons. And so what would this mean from the perspective of the electrons that are being shared? How would the red dotted line change? Well, here's how the red dotted line would change. Okay, so if I have a hydrogen atom here and an oxygen atom here, this is roughly what I'm talking about. It would look like this. Okay, so I'm about to trace the motion of the electrons being shared between the hydrogen and oxygen. Here we go. And in this case, hopefully I have conveyed what I want to you, is that the amount of time the shared electrons spend around hydrogen is a lot less than the amount of time the electrons spend around oxygen. So it might be a situation like this. 10% of the time, the electrons are spinning around hydrogen, and 90% of the time, the electrons are orbiting the oxygen nucleus. Okay, and so obviously we notice here that the atoms are different. Okay. Questions so far? Questions so far? Okay. All right, now this next point I'm going to make is subtle, but it's extremely important. Subtle, but extremely important. What did we state up here at the end of last class, and right now when I'm circling with my cursor? Atoms are defined as electrically neutral, right? Atoms are defined as electrically neutral. Okay, so that means, according to our theory, hydrogen should be neutral and oxygen should be neutral. But what's happening here is that the electron of hydrogen is spending most of its time around oxygen instead of around itself, around hydrogen. Okay. All right, so let me ask some questions here. Okay. Okay. Lauren DeBoer. Lauren, could you please say hi to us?
Hello,
Morning, Lauren. How are you?
I'm good. How are you?
Okay, thanks. Hey, Lauren, could you take a look for me in your textbook on page 32, figure 2.2? Figure 32, figure 2.2.
Okay.
What I want to do is have a quick conversation with you and help everybody understand why the chemical bond between hydrogen and oxygen is of a polar nature. And what I want you to do is look at the information in figure 2.2 and answer a couple fairly simple questions for me. So, Lauren, in figure 2.2, how many protons are in the nucleus of a hydrogen atom?
One.
One. Okay, so give me a moment to just draw some things here. So is everybody following along? So Lauren just said that hydrogen atoms, according to the information on page 32, have an atomic number of +1, right? The atomic number of hydrogen is +1. Okay, so Lauren, how many protons does an oxygen atom have?
8.
8, okay. Does everybody see where we're getting these numbers? Okay, so Lauren, if oxygen has 8 positively charged protons to attract any source of electrons, and hydrogen has only 1 proton to attract any source of electrons. In other words, if there's a tug of war between team hydrogen's protons and team oxygen's protons for electrons, does it make sense that team oxygen should probably be better at drawing electrons towards itself?
I couldn't tell you honestly.
Okay, so Lauren, what charge does a proton have?
Positive.
Positive. Are protons attracted to electrons?
Yes.
Yes. So if oxygen has more protons than hydrogen, should oxygen be a better electron vacuum cleaner?
Yes.
It absolutely should, right? That's what I'm getting at. So what I'm trying to explain to you is you can actually use the atomic number information in figure 2.2 to predict where the electrons are going to spend most of their time between any two atoms that are sitting next to each other, right? Oxygen has more protons, which means it's better at drawing electrons towards itself, which is why if hydrogen and oxygen are sharing electrons, the sharing is going to be unequal or uneven. Most of the time, the electrons are going to move towards the oxygen because the oxygen has more positive protons available to attract the electrons towards itself. Thanks, Lauren. You did a good job. Okay. Now I can write this down in your notes, but question in the chat window. Am I making sense? Are you with me here? Okay. What questions do you have that I need to answer for you? You know, the question becomes, why are the electrons spending more of their time around oxygen? Well, because oxygen has more protons. Okay. Okay, Veronica, thank you. All right, so let me just make a quick statement here in your notes about this, and hopefully when you're studying it in the future, you'll kind of remember what I was talking about. Let me make this a nice blue color here, okay? Electrons are pulled towards oxygen because oxygen has more protons. In other words, the atomic number of oxygen is greater than the atomic number of hydrogen. The atomic number of oxygen is greater than the atomic number of hydrogen, which explains why oxygen is better at pulling the shared electrons towards itself. Okay. So, any questions? Right, so please understand that the comments here in green are referring to the atomic numbers, right, of these atoms. The atomic numbers is the number of protons. The red here is the motion of the electrons, trying to simulate it, right? Electron motion. Okay, and so I'm going to ask you to take a look at something. Chapter 2, page 36, figure 2.5, figure 2.5, figure 2.5. Picture E at the bottom. Picture E at the bottom. An oxygen atom plus 2 hydrogen atoms is used to build a water molecule. Do you notice that when you look at the water molecule, you see the hydrogen atoms and the oxygen atom? But do you also notice that there's some really weird looking symbols? And here's what I'm going to do. I'm going to draw these symbols in for you at this time. And I guess I will draw them in as light blue at this point, since I'm kind of going crazy with colors. Do you notice from your textbook that the oxygen has a symbol that looks like this? And hydrogen has a symbol that looks like this. Do you see that? Do you see what I'm talking about? Okay. So these symbols are Greek symbols which refer to the phrase partial. What I'm saying is, when oxygen pulls electrons towards itself from hydrogen, and the oxygen of hydrogen, the electron of hydrogen spends more time around oxygen, oxygen starts to take on a slightly negative characteristic. So this means partially negative. And this means partially positive. Okay, what we're saying is, when a polar covalent bond forms, the atom that has electrons spending more of the electron time around itself is going to take on a slightly partially negative characteristic, because the electrons are spending more of their time there. Whereas the atom that is kind of losing the electron more frequently, in this case hydrogen, the electrons are leaving the hydrogen, which means the electrons are not available to balance the protons in the nucleus of that atom, so that atom takes on an overall positive charge temporarily. Okay. All right. Thoughts, questions, confusion? Oh. All right. You let me know as you spend some time on this with your own private study time, okay? All right, so now let's see here. Okay, all right, let's continue. We have one more type of bond to think about, and it's down here, and it is hydrogen bond. Okay. All right, a hydrogen bond. Let me give you the definition for it. A hydrogen bond, the definition is going to be very fairly long, wordy English statement, but it is what it is, and then we'll talk about it. Okay, a hydrogen bond is an attraction created by a partially positively charged hydrogen atom and a partially negatively charged atom, which is often oxygen. It's not always oxygen. It's often oxygen nearby. Okay, an attraction created by a partially positively charged hydrogen atom and a partially negatively charged atom, often oxygen nearby. Okay. So what we're going to talk about here is definitely related to the idea of polar covalent bonds. Let me see how badly I can confuse you. Okay, here we go. So let's talk, let's do a little drawing here. All right, so I'm going to draw this. Okay, up here I have one water molecule, right? One water molecule. Okay. Okay, so Jay Sanchez. Jay, could you please unmute your microphone and say hi to us?
Hola.
Good morning, Jay.
Morning.
So Jay, a question for you. Looking at your screen where you see that one water molecule,
Mhm.
Jay, can you tell me how many hydrogen bonds are present?
4.
4. Okay, stay with me. I'm picking on you. That's my job. Okay.
I think you count the one in the middle.
Okay, so Jay, I'm not asking you about your textbook. I'm asking you about the picture on the computer screen.
Oh, I'm sorry, 2.
Okay.
2.
So, all right. So Jay, let me just confirm what you're telling me. You're telling me that the water molecule on the computer screen you're looking at has 2 hydrogen bonds. Is that your final answer?
No, I changed my answer. It has none because the 2 hydrogen bonds or hydrogen atoms are bonded to the oxygen atom, not to each other.
Okay, I'm starting to like what you're saying, and I'm glad you changed your answer there. I'm very glad you did that, okay? You did fine, okay? Just relax. Thanks for your efforts today. All right. So the first point is this one water molecule has no hydrogen bonds because these bonds up here as currently drawn, okay, as currently drawn, now I'll stick with blue, right? These bonds are not hydrogen bonds. So anybody, open question to anybody that's brave enough to unmute your microphone and say, hey, tell me, what kind of bonds are these bonds that I've just circled in a blue rectangle? What kind of bonds are they?
Covalent?
Okay, Jay, what kind of covalent?
Double.
No, that's not what I'm fishing for.
Single covalent.
Okay,
Is it non-polar?
all right, that's what I'm fishing for. Do you notice up here with polar, it was HO? Down here, it's HO as well, twice, right? So I have 2 single covalent bonds that are polar, 2 polar single covalent bonds. Okay. All right. Now, let me do this. So now we're going to continue. Is there any questions? We're going to continue, and I'm going to draw a second water molecule up here. Okay, so I have two water molecules on your screen at this time. Each water molecule has its own polar covalent bonds, right? Each individual water molecule has its own polar covalent bonds. Now, what we know from our previous conversation just a moment ago is that when you have a polar covalent bond between a hydrogen and oxygen, the electron of hydrogen spends most of its time around oxygen, which causes the oxygen to take on a partial negative charge. So I'm going to draw partial negative charge. And the electron that's spending more of its time away from home, away from hydrogen, is going to cause the hydrogen atom to take on a partial positive charge. So I'm going to have partial positives around each of the hydrogens. And you know what? That's going to happen. That response that we're just diagramming right now is going to happen around each water molecule. And so what have we created here? We've created two water molecules that are polar. Okay, so let me ask a question here. Let me see. Mark Yand. Mark, can you say hi to us?
Hello.
Hi, Mark.
My mic's working.
Mark, question for you. Would you be able to tell everybody what it means when a water molecule is a polar molecule?
I'm gonna just call a blank, to be honest.
Okay, Mark. All right. Honesty is always appreciated, so thanks for trying. Can somebody help Mark out? What does it mean when what does it mean when water is a polar molecule? Anybody?
It means the electrons are uneven.
Okay, it means that the electrons are unevenly shared. That's true. Okay. Christina, you say in the chat window, there's an unequal sharing of electrons. That's true. Okay. All right. So here's what I'm trying to get you to see.
It forms hydrogen bonds.
That's the ultimate outcome, Danielle, of being polar. That's true. That's a very nice observation, Danielle. Okay, but here's what I'm momentarily trying to get you to appreciate. Okay, because of the unequal sharing of electrons within one water molecule, notice that the entire water molecule has an area where it's positive on one end and negative on the other. The second water molecule is positive on one end and negative on the other. So for one water molecule to be polar, it means that there's one end of the water that's positive and the other end of the water that's negative. Okay. Water is a polar molecule, meaning it has a partial negative and partial positive end. Well, why does it have a partial positive and partial negative end? Because of the polar covalent bonds. Okay, because of the polar covalent bonds, right? The polar covalent bonds that are present within each individual water molecule cause the entire molecule to have a positive end and a negative end, which makes the water a polar molecule. Then what will happen, and let me let me erase something here that's in my way. Okay. So let me redraw that differently for you so that you can see it. Okay. All right, so let's make this hydrogen have its partial positive over here so it's not in my way. Folks, what I'm trying to get you to see is when you have two water molecules or two of anything that are individually polar, okay, what you will do is create a scenario where you have a negative end of one molecule sitting next to a positive end of another molecule, and that is the foundation for the attraction, which is the hydrogen bond. Okay. All right. I'm not going to beat you up too much more about this. I know this is kind of heady stuff, particularly when we're not chemistry majors, but it's very important that we start thinking about this because, you know, water is a very important substance to our body, right? About 65 to 70% of our body mass is water mass. If you weighed 100 pounds and you know, if you went on a scale and you weighed 100 pounds, roughly 65 to 70 of those pounds would be water pounds, okay, just due to the water that makes up your body. So here's a statement in the chat window that I would like to get some feedback from you on. Okay, so I'm going to create a true or false statement. Okay, here's the statement. Here we go. True or false? I want you to tell me. Here it is. It is impossible to create hydrogen bonds when the molecules next to each other do not have atoms joined by polar covalent bonds. Okay. All right. So I appreciate those that are participating here. And I really do. I want you to look at the community of responses, and you notice that we do have some disagreements here. The answer to the proposed statement in the chat window is true. It is true. Okay, let's look at this again. Okay, it is impossible to create hydrogen bonds when the molecules next to each other do not have atoms joined by polar covalent bonds. That is true. Let me explain why that is true. Okay, if the bonds that are in the blue rectangle were not polar covalent bonds, then the water molecules would not have ends that have different charges. There would not be a hydrogen end with a partial positive, and there would not be an oxygen end with a partial negative. So if we don't have polar covalent bonds, we're not going to have a polar molecule. And if we don't have a polar molecule, we don't have one end of a water molecule being negative and one end of a second water molecule being positive. There's no foundation to form the actual attraction. There's no foundation to actually create the hydrogen bond. That's a lot of word to try to express some complicated things. So I don't think I want to dig too much more deeply, but let me ask you, do you have questions? Sometimes it takes some studying before you even are aware of what you don't understand, right? Sometimes it takes some studying to figure out what your questions are actually going to be. So I want to encourage you during your study time in the next you know, throughout the entire semester, but particularly in the next weeks, as we start to approach our very first lecture exam in the course, which is still a good distance away, but it'll come quick. I want you to write down questions that are bothering you so that we can talk about them. Okay, so Phelan is saying, could you explain why the answer is true again? Okay, so let's do this. Let me take this statement I put in the chat window and let me put it in your notes, and then let me offer an explanation. Okay, so hold on a second. If I could get my technology to work, come on. Oh, this is so irritating. Now. Microsoft Word is okay, but it's not great, that's for sure. Okay. All right, let's try this. True or false statement? It is impossible to create hydrogen bonds when the molecules next to each other do not have atoms joined by polar covalent bonds. Turns out that this is true. Okay. Why is this true? Okay. Here's the reason. Okay. Each individual water molecule will not be polar if the bonds joining hydrogen and oxygen within each water molecule. Each individual water molecule will not be polar if the bonds joining hydrogen and oxygen within each water molecule are actually non-polar covalent bonds. Okay. Each individual water molecule will not be polar if the bonds joining hydrogen and oxygen within each water molecule are actually non-polar covalent bonds. Okay. If water is not polar, then there is no basis for hydrogen bonds form. Okay. Okay, Jay.
So does that, okay, so the analogy I'm thinking of is like batteries where they have a positive and a negative end, and you can't put the positive end of a battery to the positive end of another battery and get a charge from it. It always has to be positive to negative, positive to negative.
Well, what you say is true. I'm not sure it entirely is an appropriate analogy here, right? If you put two positive ends of a battery together, you know, positive charges repel each other. They're not attracted to each other, right? So in our water example here, the water molecule on top, the bottom oxygen has a partial negative charge. On the bottom water molecule, the top hydrogen of the bottom water has a partial positive charge. So we have a negative sitting next to a positive, like the positive end of a battery sitting next to the negative end of another battery. That allows the current to flow through the batteries, if that's what your analogy is. This allows for the attraction between the two water molecules to form, which is the hydrogen bond. Yes. Okay, other thoughts, points of confusion, questions? So, question in the chat window. Question in the chat window. Come on, smile, come on, you will get through it, okay? All right. Nobody wants to answer that, right? Come on, I know I would be, okay? All right, so, all right. You are at the beginning of your journey to move into your future career, right? There's going to be some struggle along the way. There has to be, to understand. Okay. All right. Okay, folks. So we're done talking about chemical bonds, right? So I spent an hour talking about chemical bonds, and I spent, maybe 10 minutes the last class. So we spent a lot of time on chemical bonds. All right. Next major topic that I'm going to move to is actually talking to you about water on pages 40 and 41 of your textbook. I want to talk to you about water. Folks, whether you realize it or not, there's a reason that I stage my lectures, why I present the information in the order and sequence I do, because I started with ionic bonds, I moved to covalent bonds, and I emphasized the polar covalent bonds with hydrogen and oxygen. By doing that, I hope to give you a foundation to understand the hydrogen bond. And by understanding the hydrogen bond, you begin to understand the relatedness between water molecules. Well, if we start thinking about water, that moves us into the next talking point, which is water itself, right? Your book makes a pretty big deal about some of the properties of water on pages 40 and 41, which is why I've staged the conversation in the way I have today. All right, because again, about 65 to 70% of your body mass is simply due to the presence of water. So many of the properties of life that we get to take for granted and just enjoy are achievable because we're basically big sacks of water with two eyeballs. Okay, if we were not big sacks of water with two eyeballs, life would certainly be very different than what it currently is for us. It's even arguable whether life could exist at all. Okay. All right. Important biological properties of water. Okay. Once again, I am on pages 40 and 41, and it probably spills over into 42 as well. So some things to keep in mind when we're thinking about water, okay? All the chemical reactions that take place in your body, the trillions and trillions of reactions that are happening every second in all the cells of all that make up your entire body, the chemical reactions in the human body take place in the presence of water. Okay, I'm going to put a question in the chat window. Question in chat window, and I really want an honest response from you. Okay. Give me an honest response. So far today, have you given any conscious thought that was supposed to be thought to the air in the room you're sitting in? And maybe some of you had, because maybe the air in your room is warm or cold. Maybe the air is dry or humid, right? Okay, so some of you have said, yes, I've thought about the air in the room. But folks, look at the majority of responses in the chat window. For most people, the answer has been no here. And that's typically what I see, is the answer is no. And the point I'm trying to make is, we go through our daily lives, generally speaking, ignoring the air in the room, unless for some reason we're uncomfortable, right? If we're uncomfortable, then we think about the air. But other than that, we kind of ignore that the air is even there. We take it for granted that it's there. We simply inhale it and exhale it several times a minute, okay? That's the way water is inside your body and inside your cells. All the chemical reactions taking place in the cells of your body take place in the presence of water. And what I'm trying to say to you that is water is not a passive bystander. Water is not a passive bystander in the chemical reactions. Water participates in the chemical reactions and allows the chemical reactions to actually work properly. Now, we are not, this is not a full proper biochemistry course. That's not what this course is. So I'm not going to be throwing a lot of complicated chemical reaction equations at you or anything like that. I'm not going to do that. We're not ready for that. But what I am going to say is that please don't forget that all the important chemistry that's taking place inside your body at this time, such as the breakdown of the food molecules that you ate for breakfast, would not be possible if water was not present. If water was not present, breaking down the food molecules that you just ate for breakfast would not be possible. Water is not a bystander. It is an active participant in the chemistry of your body. Okay, folks, question. When I say this, and I emphasize that water is so important for the chemistry, let me ask you this in the chat window. Is it any wonder that dehydration is a major danger / threat to your life? If you don't have the proper water content in the body, the chemical reactions of your body cannot function correctly. Let me say this, and it's only from personal experience. I'm probably older than most of you folks, and I'm at the point where my parents' generation is getting sick and starting to die. I've experienced several episodes in the past couple of years of family members that are older getting so dehydrated that they needed to be placed in the ER to be put on an IV bag. Okay, what I'm saying to you is this: as we get older, as we age, sometimes it's harder to stay hydrated. It's easier to become dehydrated in ways that are slow and subtle, and all of a sudden the person doesn't even realize they're dehydrated, and all of a sudden, my God, they're collapsing and they need to be taken to the emergency room. Dehydration is a serious threat for everybody, but it is particularly a serious threat for the elderly. So don't forget that when you're around grandma and grandpa. Encourage them to drink proper fluids. Now, we'll talk later about what dehydration really means. When you're hydrated, it doesn't just mean you have proper water. It also means you have proper electrolytes like sodium, chloride, potassium, which are needed for your molecules to function correctly. But that's a conversation for another time. Suffice it to say, water is super mega important for your health. Okay, you should be drinking lots of water every day. Okay, so to give you some examples here of how water participates in chemical reactions. Okay, let me see if I can do this. Hold on a second. I'm going to skip around a little bit in your textbook. Okay, so how does water participate in chemical reactions? I'm not going to expect you to know the chemical reactions themselves. I'm not going to expect you to draw them out or anything like this, but let's take a look at figure 215 on page 47 of your book. Take a look at this. Okay. Sometimes water molecules are created so that you can link two smaller molecules together to form a larger molecule. Okay, so sometimes water is created so that smaller molecules can be chemically linked together. Okay, this is called dehydration synthesis. All right. So for just to get everybody participating here, okay. Figure 215. Figure 215, what molecule is formed through dehydration synthesis? Can you type that into the chat window? What molecule is formed through dehydration synthesis? What is your book showing you? Okay, good answer, Tony. Tony's the first to get it, and he's absolutely right. It's sucrose, right? Sucrose is a disaccharide. It's a very small carbohydrate, okay? Nicely done. All right, so now if you've oriented yourself properly to your textbook, you can see the sucrose was created by actually pulling the atoms off of glucose and fructose that will build water, and in the process, you also build sucrose. Okay. We're getting close on our time here, but let me continue. Okay, sometimes water is itself broken down when it is used to break other bonds apart to actually break large molecules into small molecules. Sometimes water is used as a molecular bullet to smash large molecules apart to form smaller molecules. Okay, it's the exact opposite reaction you see on figure 215. If the first reaction we described is the forward reaction, the reaction I'm talking about now is the reverse reaction. This is hydrolysis. Okay? So dehydration synthesis and hydrolysis are kind of like opposites. It's like dehydration synthesis is like going forward in your car, and hydrolysis is like going in reverse in your car. Okay? All right, so water is extremely important for the chemical reactions of your body. Number two, okay, water is the universal solvent of the body. And what we mean by that, okay, so that word solvent is extremely important, okay? A solvent is, a substance that can dissolve things. So you should be familiar. Okay, so a solvent is a liquid, which in the body is going to be water, that can dissolve molecules. Okay, that means it can break them apart. It can separate some of the atoms from other atoms. And you should certainly be aware of this phrase: a solution equals a solute plus a solvent. Okay. So let's go with an example here very quickly. Okay. If we have a cup of coffee that is unsweetened. Okay. Then question one, what is the solution? Well, the solution is the coffee. Question two, what is the solvent of the coffee? Well, that would be the water. Question three, sorry, I'm going fast, but I know our time is up. Question three, what is the solute of the coffee? Well, it would be the brown pigment molecules from the coffee beans that makes the coffee a dark color. Okay. All right. So folks, we're out of time here. We have one more fantastically amazing lecture coming up on chapter 2 next week. Okay, one more lecture coming up on chapter 2. So hang in there, be sure you're reading, be sure you're studying, make sure you're doing practice questions, right? Figure questions, the critical thinking questions in your textbook, doing Wally Plus questions that have been suggested. Try to do questions as much as you possibly can. Okay, so folks, do you have any questions before we log off today? Okay, gang, have a nice weekend. Study hard, and I'll see you next Tuesday, okay? Have a nice weekend.
Thank
You too, thank
you.
Bye-bye.
Could I possibly see the first slot, the first half you went over? Because I missed the first half because my internet was down for partially this morning.
Okay, Mark, I will post the notes in Wiley Plus, so you'll actually have all of them that you can bring down to your computer, okay?
All right, thank you. Thank you.
Do you know how to get to them?
I believe so, yes.
All right, so yeah, they'll be posted later this afternoon.
All right, thank you.
See
All
you
right,
later.
you have a good day.
You too.